Uh, then we will discuss the artificial intelligence in mobile robots, which is a whole new area, and some content related to the artificial intelligence, such as natural language processing, computer vision, and after that, we are going to talk about the robot navigation using mapping of spatial information. This is not going to be a very deep one, but we will discuss the techniques, uh, not the algorithms or any mathematics in this lecture. Uh, okay. So, what is a robot? There are actually several definitions for robot. The Robot Institute of America defined a robot as a programmable multifunction manipulator designed to move materials, parts, tools, or specific devices through variable programmed motions for the performance of a variety of tasks. That's the definition of Institute of America. There are several definitions. Another definition describes robot as the intelligent connection of perception to action. So that's a short one. Uh, However, we can say in conclusion, a robot is a machine uh, that able to extract information from its environment and use knowledge about its world to move safely in a meaningful and purposeful manner. So robots robot can or should operate on their own without human directly controlling them. That's what we are hoping for the future. And even today, there are several brands of robots that can actually operate on their own, but that's not very much for now. That as you can, someone's microphone is on. As you can, there are several new generations of robots currently used in homes, workplaces, and communities, like Pepper Robot, Asimo is not on the market, however, and there are Ibo Robot, Vector Robots. There are several robots, and those robots are providing support in various sectors like service sectors, entertainment sector. Uh, there are there are robots that used to teach to children, so that's education sector. And there are robot manipulators like Kuka, Kinova in manufacturing sector. However, those are not very intelligent though. uh, they are they can do somewhat like a predefined task, but they cannot operate on their own. Human have to program those robots to do a specific task like pick and place or something like that. Most of the manipulators used in manufacturing sector are not very intelligent. We can't categorize those robots as intelligent. And there are some assistive robots in personal healthcare. They possess some capabilities which can be categorized as intelligent, like they can initiate uh, conversations, they can respond to some questions, and some can identify objects and navigate without human support. So those are intelligent tasks. And if we look into the history, the first industrial robots actually developed in late 1950, and they were used to automate repetitive tasks in manufacturing and material handling. Uh, those robots are actually very simple mechanism. They are not very complex. Most of them use some expert systems actually not very much AI like. However, autonomous robots, which we can say that robots that can operate on their own, invented in late 1960. But it is not until recently that robots are used for practical purposes, like autonomous robot applications in couriers, in hospitals, security guards, lawnmowers. Uh, they are actually practically in use in current industry. Probably the most important application in use of autonomous mobile robot is a hazardous environment like minefield or inside a nuclear plant during cleanup of Chernobyl disaster. I think you clearly hear already that Chernobyl incident. Uh, those are not habitable to human because of the radiation. So all the cleaning is done using remotely using autonomous robots. So okay, so now we have our first assignment. This is easy one. And this is just to keep you in touch with the lecture. So I'll give you some minutes, like around 10 to 15 minutes. Uh, you, you can mention which areas or sectors that mobile robots can be applied. You have to mention the sector and how the mobile robotics can be applied. This is just to uh, get an idea about mobile robot working. So think about it and just write what you think about this question. I will give you several minutes to do that. Then we can continue. You have to submit the answers for these questions at the end of the lecture.
morning, sir.
Yeah.
I am joining now. What we have to do?
Uh, we discussed about mobile robots and its history. You have to answer these questions, and at the end of the lecture, I will provide email, and you have to send the completed answers to that email.
Now we have right, no?
Yeah, yeah. Yes, someone raised a hand. Anyone has any question?
Yes, sir. Do we need to write an essay type answer for this question, or
No, no.
just to let
Point
the
wise is okay. You have to name a sector and you have to write how the mobile robot can be applied to that sector for which task. You can point down one, two, three, four, and write down at least five or six. That will
okay,
be enough.
okay, okay, sir.
Is it on to describe that sectors?
No, you don't have to describe it. You have to just write the sector and
Yes.
you have to write a sentence or two about how the robot can be applied for which
Oh,
task, like that.
okay. Okay. Thanks.
Okay, I think you had enough time. If you have to write it more, I will give you some time at the end of this lecture. Okay, let's see some examples for mobile robots. This is the Pioneer robot platform, and it's a modular mobile robot platform with including industrial machine and gripper, and there are some equipment we can combine with this platform like vision sensor or depth sensor, and this platform also have sonar sensor to avoid collision. Uh, and there are actually several sensors, and sonar stands for sound navigation and ranging. So from sound, and NA from navigation, and R from ranging. That's how sonar is combined. And sonar sensors measure approximate echo distance to nearby obstacle, and it provides useful information about objects very close to the robot, and is often used to fast emergency collision avoidance. We can avoid collision with another object by identifying the obstacle beforehand it gets collide with the robot platform. And another useful thing about the sonar sensor is, rather than instead of avoiding the obstacles, it can also be used to map the robot environment over a larger area. In a dynamic situation, we can map the obstacle in around the robot platform using sonar sensor. To do that, we need array of dozens of more sonar sensors fitted around the perimeter of the robot, each pointing in a different direction. And this array is called a sonar ring. And this one is a robot manipulator. You can see this one is actually a KUKA robot, which is often used in the industry. A robot manipulator is an electronically controlled mechanism consisting of multiple segments that perform tasks by interacting with its environment. They are also commonly referred as robotic arms. There are another robotic arm called Kinova, and these are not intelligent. We can't categorize these robot as intelligent, because these kind of robot arms or robot manipulators are designed to do a specific task, like we can place object, or do welding robots as a so it is pre-programmed and can do only a specific task. And this one is called AGV, or automatic guided vehicle. There are actually a lot of guided vehicles, and this one is the newest generation of AGV called which is used by Volvo to transport motorbikes from an assembly station to another. And the navigation of this robot is done using an electrical wire installed in the floor. However, if an obstacle found in its course, it possesses capability to leave the wire to avoid that obstacle, and again back on the wire, and guide through it. This one is called Forester robot. Fastech company is developed the industrial light walking robot. This one, rather than the other robot which have wheels, this one has legs. it can walk, so that it can move around in the forest or outdoor environment. And the leg condition is automated. Even though the leg condition is automated, the navigation is still done by a remote human operator. So it's not fully autonomous. I think this is the most famous one. This one is called Asimo robot. Which this has more human-like interactions and human-like response we can expect from this robot. It can walk, and even it can dance. That's a very complex scenario, but the developers achieved it. I think it took very long time. However, this one possesses more human-like behavior than all the other robots. I think uh, even Boston Dynamic one is not completely capable of performing all the tasks that Asimov can perform. Okay, this one is also popular in mostly in Japan. Uh, this is a semi-humanoid robot manufactured by SoftBank Robotics. It can actually read the emotions of its user, and we can see commonly use these robots in Japanese stores, and the we can also buy this in the market. It costs around $110,500 per robot. And this is the world's first social human robot, which can recognize faces and use basic human emotions. Pepper was specifically designed to optimize the human interaction by engaging with people through conversation and its touch screen. Okay, these two are also in market. I think Atlas is not yet, but the Spot robot, which shows dog-like behavior, is in the market. And currently, the police departments are using Spot to inspect suspicious package and environment for hazardous material or explosives, to assess hostile threats remotely, and to search the structural dangerous environment in emergency response scenarios. I think videos of sports and Atlas dancing is very popular in the internet these days. And Atlas is humanoid robot that designed to move over rough and uneven terrain. It can walk through a staircase, or indoor environment or outdoor environment. It is stable enough to open two limbs and leave the other two for other activities. So it shows that it can move like very close to human. And this one is currently developed by University of Moratuwa, which is called MyRob. This research project is being conducted with the intention of developing a human-friendly service robot. The most focused, we are more focused in making this robot a more human-friendly, to assist elderly or disabled persons in mostly domestic environment. So we are using experience-based learning models to achieve human-like adaptive friendly capabilities to service robot. I will explain it later. Here you can actually see some sensors. This one is Bumblebee sensor, which is vision sensor. It has two camera. So this sensor possesses stereo vision. So we can combine these two inputs to identify the not only the object but also the distance between the vision sensor and that object. So we can calculate the position of the object, and the this one, this is the vision sensor that comes with the expose. This one is Kinect sensor. Uh, it also capable of identifying the depth or the distance between object and its vision sensor, but the techniques used by these two sensors are totally different. The first one use stereo visions to calculate distance, and second one use IR sensor to calculate the depth. And here we have manipulator, robotic manipulator, robot arm with 60 degree of freedom, and this one is laser range finder. This one emits laser and calculate the distance between the objects using the its reflection. And this is the Pioneer platform which I show you previously. By combining these sensor inputs and fusing those inputs, we get the inputs that required to train this robot to uh, show the human friendly behavior like conversations, navigation, and pick and place tasks like that. Okay, this is the second one. Uh, now you have to write down 5 different type of tasks. It can be in industry like manufacturing sector or education sector or healthcare sector. You can use one sector, several sectors. You have to identify tasks. As an example, in manufacturer industry or manufacturing sector, the robot should be able to, some robots should be able to do pick and place tasks.
Story.
Sorry, I couldn't hear that.
Story. Story.
Uh, are you giving me an example? Okay. You have to like that. You have
Excuse
to.
me, sir.
Yeah.
Sorry for the interruption. Is this also we need to include as the next assignment question, and we will reply for this one in the same document?
Yeah, yeah. There are 3 assignments.
Fine.
You have to write all the 3 assignments in the same document. And after you identified the task for the mobile robot, you should write down which capabilities that mobile robot should possess in order to complete the identified task. You have to write 5 tasks and the capabilities that mobile robot should possess in order to complete the task. I'll give you 10 to 15 minutes to answer this question.
Hello, sir.
Yes.
Task mean taking measurements likewise, is it?
Yeah. Very simple task like
A simple task.
like pick and place,
Avoid
welding
objects.
process. Yeah, that.
Okay.
So for industrial robots like welding and pick and place item, there will be no any special sensors or things which we require, right? Because we need to do perfect programming. If so, he will go or he will move according to this programming. So in that case, what type of things he can mention? Because only so I have mentioned like programming is the only requirement for that, something like that. Because he don't need any ultrasonic sensors. He doesn't require any vision camera, vision based system. Because he will go to X place and he will do the pickup using vacuum or something. Then he will go to B position and he will drop that.
Yeah, you only have to write down the task, and to perform that task, which capabilities the mobile robot should possess. So you don't have to think very deep about this question. You only have to think simple task in any sector, whichever you prefer, and think about the capabilities. So in order to let's say a robot should let's say for an example, a sorting task based on the color. So robot should be able to identify the color
Okay, understood. Okay,
like
okay,
that. Okay.
okay.
Okay, I'll give you 3 more minutes, and if you need more time, you can take that time at the end of the lecture. Okay.
Excuse me, sir. Sorry for the
Yes.
interruption. Can I ask
Yeah.
you, sir, first? For an example, I have taken example. Shall I discuss with you that one for some? Hello.
Oh yeah, can you say that again? I couldn't
Yeah.
hear you.
For an example, I have taken example of one type of a task is a parcel delivery.
Okay.
So the process that I'm going to explain in a point form, like first of all, in the sequence, it will be pick the parcels. Then it has to be follow the navigation according to the delivery, like a target place, the
Okay.
destination. Then it's detecting some obstacles. Meanwhile, it's passing through the navigation to the
Yeah.
destination.
Okay.
Then it will confirm with the delivery, like the person
No.
who to deliver.
Yeah. Yeah.
Then
So
it's deliver the parcel. This form is okay.
yeah, I think the task you selected can be divided into several subtasks, right? Like
Yes.
navigation is one task. The identification of the receiver is another task. So you can divide that into several tasks.
Okay.
And as an example, if you take the navigation task, the robot should be the capabilities that robot should be possessed is like localization. Localization mean the identify the position of it on the surrounding environment.
Orientation, like.
Yeah. Like odometry data processing, those kind of capabilities.
Okay, so if we give the process, so shall I choose one of above robots? Like you have asked us to select five tasks.
5. You can.
So
I think you can take like 3 tasks from the procedure you just mentioned. 3
okay,
or 4 tasks.
I will choose any of 3 tasks. Then I will
Yeah.
explain each and all the subtitles. Like.
Yeah.
Okay.
So in this assignment 2,
Yeah.
we have to capabilities and where we used, no? We mentioned, no?
You have to mention the task
Uh,
and for to perform that task, which capabilities should the robot possess?
uh-huh.
Like
Color identification.
yeah,
Color
color
identification
identification is a capability.
capability.
That
Task
might
is
be task can be a sorting task
sorting task. That's
or a pick and place task.
That's his
Like that.
task. Hari.
Okay, I think we can move on to the next side. Those who couldn't finish the question 2, you can finish it at the end of the lecture. I will give you some times. Okay, right. Yeah, this one is very important topic. AI in mobile robots. Artificial intelligence is what make mobile robots intelligent. As I told you before, the robot manipulators such as Kuka, Quinoa, they are not very intelligent. So what make the robot intelligent is they should be able to learn and adapt to the task. So there are several things we identify to that a mobile robot needs to use to become intelligent. As an example, if you take the learning, the goal of the learning in a robot is to prepare it to deal with unforeseen situations and circumstance that in its environment, like navigation task. The surrounding in a navigation task, surrounding environment is very dynamic, moving objects, moving people. So robot should be able to learn its environment and adapt to the dynamic of that environment. The fact that even the simplest of animals seem to be adaptable suggests that learning must be important for survival in animal world. So there are two main benefits of learning. If we take an biological system, which is most of the time inspired researchers to build robotic system. So in biological systems, first, learning lets the animal adapt to different circumstances in the world, giving it a wide range of environmental conditions in which it can operate effectively. Second, learning reduces the amount of genetic material and intermediate structure required to build in the complete functions of an animal. In some circumstance, it is simpler to build a small structure capable of constructing a larger one. So that's why I asked you to identify the subtask of an larger system. After you identify the subtask, you can amalgamate it to build a larger system. So there are several knowledge bases in learning systems. The first aspect of learning in animal directly applies to robot as well. We would like our robots to adapt to changing external circumstances and adapt to changing internal circumstances, like drift in a sensors and actuator, loss of power, and perform new tasks when appropriate. And the another aspect is that the second aspect does not transfer directly to robot control unless they are programmed using genetic techniques. So we can distinguish these three types of knowledge that would be useful for a robot to acquire. There are hard to program knowledge, as you know. Information that is very difficult to program by hand may be obtained by showing example or guiding the robot. Like there are object recognition. If you, I think you have seen these are very popular in internet. If you write a program to identify dogs from cats, if you given a lot of pictures of cats and dogs, a human can identify which images are the cats and which images are the dogs easily. However, a computer or robot find it's very difficult. Like if we show some 3 or 4 cats to a human and totally different cat in the sixth picture, a human can identify it as a cat. But in order to robot to identify a cat or distinguish cat from a dog, it required very complex programming, which we can say very hard to program in conventional method. And there are also unknown information. The information necessary to program the robot is simply not available. For example, a map of the terrain the robot will be working in. We ask, for an example, we ask the robot to go to another building and perform some task. So the destination is totally unknown to the robot. That can be explained as unknown information. And change in environment. The environment is dynamic place. Even if we had a complete model of the environment to begin with, the knowledge could quickly become obsolete in a dynamic environment. Also, slower change can be occur, such as calibration of the robot on sensor and effector. But I'm not talking about that. I'm talking about the dynamics of the environment, like objects are moving, it's not static, but and also the humans are moving. So the maps, if the robot create a map of an environment, it will be changing the next movement. So the details will be changed, and robot should be able to adapt to that scenario. Yeah, okay. And then there is reinforcement learning. Reinforcement learning is a very popular technique used in robots. It has been applied to learn new behaviors and to coordinate existing. At the moment, I think it is the probably the most popular way of learning in robots. Reinforcement learning systems attempt to learn a behavior by exploring all the actions in the available states and rank them in order of appropriateness. It uses reward or a punishment to alter numerical values in a controller. A component capable of evaluating the response is need to send the necessary reinforcement signal to the control system. Like let's say you need to train a robot to pick the only the plastic bottles. So what you do is you program to pick any object, and you give a plus point when robot pick up a plastic can, and a minus point when it pick up any other thing. So after robot evaluates the points given to him, those are the reward. If it's a +1, it's a reward. If it's a -1, it's a punishment. Then robot try to collect more plus points, which will end result in robot only pick up the plastic things. So the feedback to the control system, which is the reinforcement, provide information about the quality of the behavior response that robot create. It may be very simple as a binary pass fail, or as I said, plus or minus, or more complex numeric evaluation. And there is no specification as to what the correct response would be, only how well the particular response works. And then there is artificial neural networks, which will discuss in later slides. And again, there are fuzzy controls, which are used to interpret uncertain information. We'll discuss in the later slide as well. So this one we call deep learning network or artificial neural network. In this lecture, I'm only giving you a basic understanding about these techniques. I'm not going to discuss in details. However, deep learning networks are used to create connection between inputs and outputs. We already know, and use that connection to predict another input. Like, let's say you have let's say you have data about house prices. Say you have data about a table like this. You have square meters for the area of the house and number of rooms and let's see the nearest bus station, distance to the nearest bus station, and the price of the house. So you have several data for each column, which can be collected, and you need to predict another house which is not in the table, but you have A, R, B, an area, the number of rooms, and the distance to the nearest bus station. So based on these values, you need to predict the new one. So we can use deep learning network to predict these. These are the input layer. This one can be the number of rooms. This one can be the distance to the nearest bus station, and this one can be area of the house. So in here, only 3 inputs are mentioned, and the output should be the price of the house. So here's the output layer. So if you are going to create a neural network for this task, you only need 3 inputs and 1 output. These are called the hidden layers, and this one we call perceptrons. The neural networks are inspired by the human neuron. So this is proposed by Jeffrey Hinton in 1986, and this is a very popular technique used in the current research community. So what neural network does is it connects inputs and outputs by adjusting the weights of these parameters. It adjusts these parameters to match the inputs to output. After training for several inputs, we can use the predicted we can use the trained model to predict new inputs. Okay. So what artificial neural is do is in the real world, it is very difficult to learn hand program algorithm. So like you can't write if and else program to get the result for this kind of program. So it's very difficult to learn with hand program algorithms. The continuously changing environment and uncertainty caused by these changes require flexible learning system, and artificial neural networks provide this. So learning in neural network occurs through adjustment of synaptic weights. Synaptic weight means these weights. These R1, R2, R3, and A1. These connections are made through synaptics. And and the neural networks are learning through adjusting the synaptic weights by error minimization procedure. So in order to minimize the errors, neural networks use several algorithms like optimization algorithms, which I'm going to explain later. So in conclusion, you can use neural networks, the artificial neural networks to solve problems that are difficult to solve by hand program algorithms. That's what I need to tell you. The conclusion is you can use deep learning networks to solve problems that difficult to solve with hand program algorithms. Okay, there are several types of neural networks used for several tasks. I will explain it in next slide. Okay, these are the some types of neural networks. You can see convolution neural networks. Convolution neural networks are used to for image processing tasks, object identification, optical flow analysis, or like object tracking and object segmentations from image. For that, we use convolution neural networks. And here, recurrent neural network. Recurrent neural networks are used to process sequence data, like weather data or sentence patterns, analyze sentence patterns. To do that, we use recurrent neural networks. And commonly for common tasks, we can use deep learning networks such as artificial neural networks. There are several other types of networks like restricted Boltzmann machine, generative adversarial networks, and self-organization mapping. And there are some other networks which I didn't mention here, like probabilistic graphical methods, PGMs, like that. But most commonly used neural networks are these three: convolution neural network, recurrent neural networks, and artificial neural networks. I think we can discuss some details about these networks in later lectures. In this lecture, only recognizing the names should be enough, I think. I just want to familiar with these names with you. These are the neural network algorithms that used to train neural network. Most common one is gradient descent method. This one is most popular optimization algorithm in the field of artificial intelligence. And most of the time, I think 80% of the time, we use gradient descent. And there are the algorithms as well, such as conjugate gradient method, quasi-Newton method, and Newton's method. Those three are not very much popular. The most popular one is gradient descent method. And another aspect of mobile robots are natural language processing. A robot should be capable of, for an example, assistive robot should be able to make conversation with the users. And if the conversations are very predefined sentences, we get bored. So it should be, a robot should be able to respond to our questions accordingly. And for that, it requires natural language processing. These are the applications of natural language processing, like text processing, name entity recognition. Name entity recognition means if we write a program to identify the let's say we have a storybook and we need to identify all the character names. So we enter the storybook into our program, and the program should be able to identify characters, human characters, and specific building names or road names, such that. And that's we call name entity recognition. And text classification. And creating conversations and uncertain term interpretation, and explaining, like image captioning. If we give a image, the robot should be able to tell what's in the image. If you are familiar with the Facebook is capable of self-captioning the images. For an example, let's take that this sentence. There is a cat near to the table. As we can see, there is a cat near to the table. So the term near is an uncertain information. It doesn't give us a quantified value. Like for an quantified value, we can say the cat is the distance between cat and the table is 50 centimeters. That is a numerical value, and we know what 50 centimeters means. But humans tend to use uncertain terms such as near, far, like that. So in order to have interactive conversation with a user, a robot should be able to use uncertain terms as well. We don't usually use quantified numerical values in our conversation. We say like turn left, turn right. There is a cat near to the table. And a vehicle is going fast. All those terms, left, right, near, far, middle, fast, they are not defined variables or defined values. We are defining it, interpreting those values based on our experience, based on the environmental factors, like that. Okay. This is the one I discussed with you, that humans prefer to use voice conversation and description to describe unknown environment to the robot. And descriptions and conversation include uncertain terms such as little, very little, large, near, far. And the conversation can be used to describe whereabouts of an object. And those conversations will include those uncertain terms. And we can use natural language processing to interpret these uncertain terms to a numerical values. So that's one capability assistive robot should be possessed in order to have interactive conversation with the user. These are the conventional methods to that used to create conversations between user and robot. You can see these are predefined questions, and these predefined questions are combined with this blocks diagram. You can see question flow for a robot. but this is very pre-programmed. So this is not very interactive. We might get the same answer for several questions. So the advantage of the natural language processing is we don't have to use this kind of predefined blocks to create interactive conversation. We can train the robot to learn human sentence patterns and human conversation styles in order to create its own conversation style. That's the advantage of natural language processing. Okay, the next aspect of the mobile robot is computer vision. As I mentioned earlier, computer vision, we use it to recognize objects for path identification, landmark recognition, position calculation, and image segmentation, and image classification. But actually, there are several algorithms that use convolution neural networks to perform these tasks, like object recognition. There are some countries that use traffic cam to identify the number plate of the vehicles, and if they violate the any regulations or law, they identify the number plate and use that to identify the owner of the vehicle and send a ticket to the user of that particular vehicle. And the next one is navigation, mobile robot navigation. So navigation task is simply going from one particular point to another particular point. And when a robot or a human have to perform a navigation task, it ponder these questions. Where is the destination? Where is the starting point? Where are the end point or the destination? And what is the destination point? What is there? And how we get to A from, how we get to B from A. So answering this question helps robot to perform a navigation task. We can divide the navigation task into two categories, like indoor or outdoor. The difference is indoor environments are more structured and outdoor environments are unstructured. Indoor environments include transportation and customer support in museums and shops, cleaning robots in large buildings, and robots in research facilities. Outdoor environments include mining or switch tubes, agriculture sector, navigation in forest or in a construction site, and there are also military tasks like finding things in hazardous environment, identifying landmines. Those are outdoor environments, and there are some robots that can perform navigation tasks in both environment, indoor and outdoor. This one is assistive wheelchair we developed in University of Moratuwa. You can see several sensors we include to perform the task I mentioned earlier. Here we have the leap motion sensor. I will explain it later. This sensor can recognize the hand gestures. And here we have laser scanner, which emits the laser beams and calculate distance based on the reflection of the emitted laser beams. And here we have industrial machine. All the inputs are sent to the this machine, and it will process those data to interpret raw data into the information. Okay, here you can see a gesture model we created to navigate the wheelchair, the previous one, this one. This gesture command, based on this gesture command, the wheelchair can be navigated. Each left image shows how the leap sensor see our hand. The second right on the right side, you can see the actual image of the hand, and the left one is how leap sensor sees the same hand. This is the enlarged image of how leap sensor recognize our hand. It recognizes joint in our fingers and the palm. These are the parameters we can use from the leap sensor. We get these parameters input from the leap sensor to our industrial machine. Yeah, this is how leap motion sensor works. So from the data we get from the laser scanner or sonar sensors, we forms maps. There are actually 3 types of maps, such as conceptual maps, cognitive maps, and 2D or 3D spatial maps. And conceptual maps graphically represent the data and relation between them. And cognitive maps are the visual representation of robot to acquire code and store, recall, and decode information about the relative location and attributes of phenomena in their everyday spatial environment. And this third one is the most common types of map, which is 2D spatial map. It represents the geographical data about the space at human scale. So this is a LiDAR sensor, enlarged image of the LiDAR sensor. You can see the range of that particular sensor. Here we have 275-degree range. And since it's a 3D sensor, it can identify 6 meters in height of any obstacle between 45 meters or 60 meters. This is a real image of the environment we use to create this particular spatial map. You can see this is what we see, and this is what robot sees. Here the white lines are the obstacles, and the black pixels represent the free space. So this is what we get from the laser scanner. And it's not very much to go on. So we have to enhance the image and create a most appropriate spatial map in order to navigate in an environment. So here you can see the layers, 4 layers for each height, and then we combine those layers in order to create the full map. That's shown in the E subclass C. And this is an enhanced map of that particular map. This last one is enhanced, and we get this. In here, you can see the boundaries are identified clearly. So we know now where the objects are in the environment, the positions of relative position of the object respective to the wheelchair. Here you can see the same image, but we used image processing technique to cluster the image so that we can identify the different objects. Okay. So these are all of these maps are spatial maps. Actually, 3D spatial maps. We use these maps to navigate a robot through an environment. Okay, this one is the last assignment. With the knowledge you gain from these slides, you can explain the benefits and disadvantage of replacing human workforce with mobile robot. So what we are doing by creating robot is we replace particular human force with the robot to improve the efficiency of a task. So there are benefits and disadvantages. So think of some and list them out, and you can after this you can use the rest of the time to complete previous assignment. And after completing this one, send the completed assignment to the email. I will put it in the chat. Okay. I send the email address to you through chat. Make sure you name your document with with the index number. Put the index number as the name of the document. Okay. Now you can answer the question.
Sir, excuse me. Hello. Sir.
So how many points should we have to mention over here? Is it only 1, 2, 3, or some more?
Okay, 5 will be enough. You can mention 5 benefits since there are more benefits, and
So
like
5 advantages and 5 disadvantages.
5 benefits and 2 disadvantages.
All right. Okay. Thank you.
Okay.
So how many? 5 benefits and 6?
No, 5 benefits and 2 disadvantages.
2 disadvantage.
Okay, you have another 10 minutes to complete this assignment. After that, the second lecture will be started on control system implementation. At the end of the both lectures, which means 12:30, you can submit the assignment.
Sir, can you please show assignment 1 also? I need to take a photograph of it.
Okay.
Sir, there will be any assignment for the control system also?
Yeah, there will be like 2 or 3 assignments. You can finish all the assignment and submit, let's say.
No, sir. There is any assignment in the afternoon?
Yeah, for the second lecture, there will be also assignments. You can submit before 2 p.m. All
That
the assignments.
this assignment or control system?
Both
Oh, before 2 p.m.
before 2 p.m.
Oh, okay. Oh, same email, no, sir?
No, the second one will be conducted by another lecturer, so you can send it to him.
Oh, this is for you, no?
Yeah, this is these 3 assignments for me.
Okay. So
Okay. If
Sir, can we do this all 3 assignment as in one document?
yeah, you have to do in one document. Okay, this is the assignment 2, and if you need, this is the assignment 1.
Okay, thank you.
Okay, so that's all for this lecture, and you have I think like 15 minutes till the next lecture prepare. So okay, we'll finish it now. You can submit the answers before 2 p.m. Okay.
Sir, excuse me. Why am I?
Right. Good morning, students. So I am K.D.M.Jayawardhana. I will be covering some parts of this lecture series. Right. So today our lecture is control system implementation. Right. So within next 2 hours, we will try to a modular system. Right. Mathematically, then implement it. It's in Python or MATLAB. Right. Then try to control it using PID control, right? So let's get started, right? First, we have to know what is control, right? So I think you have covered these topics in applied control system lecture, but I will give a brief recap. Okay, right. Can everyone hear me? Is my voice is there?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Right. What is control? Control is we have a we have something in our mind, right? We have to achieve something that is in this red line, right? This is what we need to achieve, right? This is, we can say this is the command, right? Right, we can say this is the command and this one is our actual value, right? What we receive from the system, right? So what we are trying to do is minimize the difference between actual and the commanded, right? Right, that is what we are trying to do using control, right? Okay,
Okay.
that is what we are do in control, right? So what is system? What is system? System is set of subsystems, or we can say set of elements which are scattered together to perform a specific task, right? That is a system. It has a boundary, it has inputs, it has outputs, right? Something like that. We can say a system. If we have, so I hope you all joining the lecture using PC, not mobile devices, right?
So I have joined that mobile.
By mobile phone, right? So can you have
I need
access?
to.
Do you have access to the laptop or computer? Because end of this section we have to program, do some Python program.
Actually, for the time, I don't have a possibilities to access
Okay,
a laptop
okay.
or something. So if you have anything, I will just follow the class. And if you have any assignment or something related to this one, can you give me some time to submit that one, not
Okay,
instantaneously?
okay, okay. I will. Right.
I have
Thank you
only
so
a
much.
download MATLAB only, sir.
Okay. We don't need MATLAB. You only need access to the internet. So I will provide
Yeah.
the platform to you to
Uh,
program. Okay.
Okay, sir.
Okay. So I saw one of you have not have a Google account. If possible, send your Google account. So I will send my program. So it will easy to work.
Or else you put that file path so that
That
we can.
that Resard does not have a Gmail account. Others have the Gmail account. Right. So Resard, if have send me your Gmail. Okay. Right. Okay. Let's start. Okay. The system is collection of elements scattered together to perform specific task. Right. Okay. So that part also we covered in applied control lecture. Right. So then they will discuss about control system.
A control system is a system which provides desired response by controlling the inputs, right? We control the output by giving desired inputs, right? If we think this as a black box, right? We think as a box, right? We give certain input from the steering wheel and we achieve a certain direction of movement from the tires, right? Right. So in here, we from the eyes, we are looking at the road condition, right? We are looking at the road condition. We are looking at the upcoming vehicles, right? So we receive a feedback from the eyes, right? Right. So this can be if a human driving a vehicle, we can say it is a closed loop system, right? There is a loop between the system, right? So we will discuss that, and there are some specific terms which are used to work with. So you guys have the idea, but I will explain these terms very briefly. We discuss the accuracy of the system, that that if we measure something, first we need to declare the accuracy of the system, right? Accuracy of the measurement, right? So then we know how much accurate the measurement is, right? Then we discuss the sensitivity of the system, that depends on the system characteristics, right? The response to the input, right? If 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 system responds to the tiniest variation of the input, that system is very sensitive, right? And there is noise. Noise are the unwanted values in the measurement or unwanted values in the outputs, right? Then stability. Right? Stability means how much our system is stable, right? If we gave some input, how much our system is stable to the unwanted inputs or uh, inputs we provide to check the stability, right? Some kind of input, we check the stability, right? That the system does not break its position or something like that, right? Then the bandwidth is the frequency the system can operate, right? Brief idea, right? We have common types of control system. So what are the common types of control system? We have continuous time and discrete time control system, right? What is continuous time control system? That in the previous years, we heard of that FM radios, and then now we have a so those different FM frequencies, right? In in that era, we use cassette tapes, right? They record values, they record sound waves in something like that form, right? What happened to those cassettes and the disc record the voice? So we discard that, right? That is old technology. We convert into digital era, right? In that era, that if we think this is my voice, right, we used to record in digital format. What digital format does is it takes the time, right? That it's wrote down this position, right? Now this is the amplitude, right? Or the voltage, something like that. We record only the amplitude, not the waveform, but only the amplitude. In T1, in T2, we record the amplitude, right? So we gave this type of amplitude, right, recorded amplitude to the system, we record this in digital bytes and gave this to the system. It produced back sounds, right? Now we can see, this system is continuous, right? There is no time gaps, right? There is no missing data, right? In the digital system, there are some gaps between the measurement, right? There are some small gaps between the measurement. There are a little bit of time variations, but these gaps are very simple, very small, right? With these small gaps, human cannot identify the difference between the digital one and the analog one, right? Same as the control, we have analog control and the digital control, right? That is first first method of separating the control system, right? So then there is another one. Open loop control and closed loop control, right? So we draw some small system here. So now I can tell this is my plant, right? I am telling this is my plant, right? Plant means some system, right? It has motors or it has some voltage device, right? Heating device elements, something like that. We call that a plant, right? So I gave an example for the open loop system as a toaster. So in our house, we have a toaster, right? What it does is it toasts bread for us, right? So what we does is we close this lid and switch on the plug. We connect it to the plug, we switch it on, right? Switch it on. Then it will take the energy and it will generate heat. And after 3 minutes, the light says it is done. Light says it is done. Maybe green. That red one is switch off and green one is switch on. So we know it is done, right? The toast is done. So what kind of operating system is this? What kind of system is this? So
Open loop.
right, this one is open loop because that green light does not know the toast is done or toast is not done, anything. He didn't know that green light, right? So he didn't care about those. Only thing he care is the time, right? Time. He thinks within 3 minutes the toast is done. I am ready to output my product, right? So those kind of things are open loop system. Then we have closed loop systems, right? So what is closed loop system? Closed loop systems are, we think of, this is my plant, right? To the plant, I have a controller, that is my arms, right? That is my arms, right? I am getting that vehicle example, right? Vehicle example, right? What I get from this plant, right? Moving forward, oh, the angle, right? Of tire, right? Angle of tire, right? So from the eyes, we receive some information, right? From the eyes, we receive some information and we send it to the brain. and process something and get the command to the arm, send the command to the arm, right? Right. The angle of tire, do we measure the angle of tire? Right. Then plant moves, right? Vehicle moves. We can see the difference in direction, right? If we, that this is my road, I was right there, I need to go somewhere here, right? So I turn the wheel. If it is not, if I going in this direction, I will turn more, right? I will turn more. So there is a angle of tire measurement using the vision sensor, right? Using the vision sensor. So there is a feedback going here to here, all right? From the vision sensor to the brain, there is a this is also the this is also vision sensor. Got it? This is closed loop system, right? We have something in here, right? We think we are going for a shop, a dedicated shop for pets, right? We saw the pet shop is there, so we need to turn now. So we saw a command, we create a command to turn, right? So we gave that command, right, to the arms, right? Arm turns the wheels, then the plant moves certain direction, and if it is correct, vision sensor detect, now it is correct, we don't need turn more, right? So if it is not correct, we turn more the wheels, steering wheel, and the our tires will turn more, and we will reach the pet shop accurate, right? So there is a closed loop system. There is a feedback from the vision sensor, right? Got it? So
Yes, sir.
right now, what we trying to do is we trying to model these plant, right? What we need to do is model these plant, right? So we now for the vehicle, we don't have a mathematical model for this, right? We don't have a mathematical model for this. So how we build mathematical model for this, right? So we can say this is my angle. This is my angle, and this is the central axis, right? If I move from the central axis, this is the full rotation, right? So I can measure this angle theta, right? In here also I can have a angle measurement, right? Theta 2, right? So by doing those kind of mathematical representation, we can create mathematical model, right? Got it? Right. Let's do some simple one. This one is too hard, right? Let's do some simple one. Okay. Right. If you need to copy this down, right? In your words, right? This can be angle of tires, or this can be angle of movement. Right. those things, I hope those things will covered in this lecture, right? That applied control system lecture, right? So what we are going to do is discuss the implementation of control system. Before doing the implementation, we need to know the mathematical representation of models, right? So let's discuss about mathematical representation, right? So there are smaller system, right? I gave a smaller system to identify the mathematical representation, right? Right. We have given VI voltage to here, right? The voltage is VI and it generates a current, right? What are the devices we have? We have a resistor, inductor, and a capacitor, right? In the image, it shows that capacitor voltage is V naught, right? Capacitor voltage is V naught, right? So how do we get this voltage and this voltage?
IR.
Yes, we can say VR equals I times R. So VL
LDI by DI over DT.
L DI over DT, right? Everyone got that? Everyone got that? How do we get this term? So we get this term by, so this is the inductor. This is the inductor. The inductor's characteristic appears, he changed the variation of the current, right? If we give some constant current, it will do nothing, right? I equals 5 amps, it will do nothing. If we suddenly move this current, right? Something like that, if we done, now it will become to act, right? This is how the inductors work, right? Right. To capture that, we do this kind of thing. This is the variation of the current. This is the parameter to variation of the current, right? For the capacitor, it says V naught. So what is V naught?
VC.
V naught is
VC.
VC, right? We can say VC, but also V naught, right? Also, this one is right. Right. Then how do we capture the current going on here and how do we get the relationship between that capacitance and the current? I. Right. There is a small equation called C V, something like that, right? QCV, Q equals CV, something like that. So what is Q? The amount of electrons in the capacitor. So it is the integration of current,
DI.
integration of current to the time, right? 0 to t. But if if current moves something like that, this is the area of current moves, right? Area under the curve, something like that is this, right? So we can say this is 1 over C. The Q part is this one. No? Then voltage we can see V naught. Can see integral of I t dt, right? So I will right. Those three equations are there, right? Those three equations are there. Now we can get the full equation, right? So how do we get the full equation? Now we have three separate equations. So Now V input equals R IT. So it varies with the type, right? Then also we can say L times D IT over dt plus 1 over C integral T dt, right? Okay, everyone got that? Or shall I need to do that again? Explain this again.
That.
Okay. So if you don't understand or if you feel you are lost, let me know. Okay. Right. So this is how we represent this plant using mathematical representation, right? Shall we stop there in mathematical modeling? No, we don't, right? So we can do more. We can do more. There is, what is S? Laplace S. This is the Laplace S. So we can represent these derivatives and integrals in Laplace format, right? Laplace format. So if we try to do that, it will become something like that. R I S plus L times this one will be written as S times I S, right? This derivative becomes S, right? Then we can see this one, this integral becomes 1 over S, right? IT, no, IS, right? In Laplace format, right? So then we can, there is 3 IS terms. So we can write R times LS plus 1 over CS, right? Right? We can represent this in Laplace format. Okay. Got it? If you need to copy this down, please copy this down. I will give some small time. Okay, right. Now we are going to do the same for a different system, right? We are going to do the same for a different system. This system is spring damper system, right? For people who have done mechanical, at least something, they know what is damper is. This is the damper. This is spring. There are damping constant and spring constants. So can you try to model this, right, by yourself? Can you try to create equations for this system? the things we can do is there is F equals ma equation, right? Forced equation. So if we gave some force to this direction, this will increase, right? This will increase. T will increase. So there is a force and x, and there is this equation also. Try to get some equation, start doing something. So I will write this down as double dot. Right, that part is mx double dot, right? We have f in this direction, and k and damping are acting on other direction, right? Then force from, this is the force from spring, right? What is the force from spring? F spring. What is the force from spring? How do we write that?
X.
I can say this is S and KD, right? Force from spring. K S times what? What should go here?
X.
X. XT, right? Then force from damper. KD times what should go here?
Minus xt.
Sorry, again.
Same
X.
XT.
X minus xt.
X minus XT. So for the damper, damper is something like inductor, right? If it is compressed, smoothly compressed, it will not create its actual force, right? If it is compressed smoothly, it will not create its actual, it will not show its actual behavior. If we change the force something like this rapidly, now we can see the, right? So there is this term, right? There is this term, right? Derivative part also there, right? So for the damper, there should be a derivative part. Got it? So we can write this down as dt dot times t, right? Okay, let's write this down again. Right. Now I can write down the equation. This is force in this direction, Fx, Ft from here. This is to here. And from the damper, I can write down this. These two is minus direction, right? I put minus direction and open bracket. From the spring, the force is Ks times Xt, right? From the damper, the force is Kd times d dt xt, right? This the force, the reaction force, that this is the remaining force. We can say this one is the remaining force. And what will this do? This create acceleration, right? In this direction, this create velocity acceleration, right? This will gain velocity. This system will accelerate to this direction, right? If the ft is sufficiently large. If the ft is sufficiently large, the system will accelerate, right? So if it is accelerating, it will create acceleration x dt square, right? And the m, and then this is ma, right? This is acceleration. Now we have mathematical model of this system, of this plant, right? If we need to do more, we can get the Laplace transform of this one, right? So we turn this term into Laplace values. This one will be Fs minus Ks times Xs minus Kd times one is S times Xs. S times times Xs, right? There is multiple Xs is here, here, and here. So we can get those values to one place, right? So you can do this part. You can create this part and Fs to here, right? Do that. Is it okay? Right? Everybody got that? Right. Right. Now you have to take a picture of your answer, right? Your answer, take a picture of your answer, your notebook, and send that to the chat, right? The Teams, Zoom chat, to this chat. I think you can upload picture.
Is it okay if we wrote down this answer on chat box?
Okay.
Over here.
Right. Good. Now only three students sent the answers so far. Others also try. If possible, take a picture of your answer and send to the chat. Right. Hope you got that one, right? Right. Now it is very simple, right? From here onwards, it is simple. Those are the hard topics, right? So what we have is m times s squared then plus kd times s plus ks, right? So I need to get rid of this m part, right? I need to get clean s square, right? Then what I will do is xs fs divided by m, right? Okay. Now I have something called a theory part, right? That says the transfer function of a model, right? Now we have a model, we have a plant, a spring damper plant, right? We can say this is the black box, right? Inside this box, we have a spring and a damper, right? This is our plant. Right. So this is our plant, right? We input fs and output xs. So transfer function is this is ys, this is fx, right? We get the value to this, something like that, right? Now for this example, we get the value xs divided by fs. Now change the equation and get the value for this one. for this plant, transfer function is xs divided by fs. And this is the transfer function. Call this the transfer function. Also, we call that as a plant model or mathematical representation of the plant, right? Right. So you have to send the answer via chat, right? Okay. 1 over m divided by s square plus this part kd times m plus ks times s. Right? What is the importance of this plant model or transfer function? Right? Why we represent the using this format, right? That output divides by input format, right? So if we write this down here, right? If we write this down here, 1 over m squared plus kd to m times s plus ks over m, right? This is our transfer function. We are saying this is our transfer function. What is the importance? So if we multiply this by, so we can say this is a simple value, right? We can say this is g, right? This is a small variable, right? G. I name this whole transfer function as G. So we get force, we multiply by G, we get the value, position, right? Got it? If we multiply this by here, we say, right? We get the position variation, right? That is the importance of this transfer function. All right? It is simplified the plant model. It is a simplified mathematical representation of the plant model, right? So we can represent this using MATLAB, right? Sure. How do we represent this using MATLAB? In MATLAB, we have special tools, right? So our discussion will not go towards the MATLAB. So because it is symbolical, right? We don't need that much of symbols in practical module. This is the implementation of control systems. So we don't need to do the MATLAB part. We will implement things in Python. The MATLAB is to just to showcase, right? Right. MATLAB will come. It is too slow. Right. Now I will give. Right. I will give a small question. Right. My m is equal to 1. Right. KD is equal to 0.5 and Ks is equal to 2, right? What will be this equation? Xs divided by Fs. So create that equation. squared KD is 0.5 plus 0.5 times S plus K is 2, right? Something like that. Right? Right. I will not go through this one, right? I will not go through this one. And this is the damping constant. Constant, and this is spring coefficient, right? Spring coefficient, right? This is the model we got, right? So now we can represent this one in MATLAB. So try to get the equation done, right? So I have the plant, right? For this one is transfer functions with or without initial state, right? So the first line is in MATLAB, the first line is the numerator, right? If we need to add S values, we have to add another value here, right? What, right? Apply, we get S here, right? Let's remove this. Let's model our values, right? In here we have S square 5 times 6. Now what we have is 0.5, 0.5, and this one is 2. Apply. Okay. Right. I gave the force as 1 and I not tuned the PID. Let's see what are the values inside the PID. Right. There is no values in PID. We will discuss the PID in a moment. Okay. We can run the model. This is online version of MATLAB. That is why this is slow. And from the scope, we can get the output. Right, something like that. If we gave a step value, step input, this is my input in blue color, right? This is the variation of the position we get, right? Got it? Right. 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 Similarly, for the current model, for this capacitor inductor models, they used to do the mathematical solve, right? Right. So let's try to model this one, right? Let's try to not to model, but to understand this system, DC system model, right? We have voltage, resistors, inductance. This is the back EMF. EB is the back EMF. Back EMF, right? And the current, the position, velocity. JB is the motor inertia, and B is the friction coefficient. That is called viscous friction coefficient, right? What is TS? That is the torque, right? That is the torque. So if we model this one, we get something like that. We get something like that, right? This is Km here. That is for Km is not represented here, right? Km is motor torque constant. Motor torque constant is not there, right? What is tau m? Tau m, motor inertia. The inertia, right? Right. Right. We don't need to model all this, but I am interested in this part, right? I am interested in this part because we can say this system gives voltage inputs. System gives voltage inputs, but we have motor controllers which can provide current inputs, right? It can control the current, can measure the current and give the specific currents we ask them to inject to the motor, right? So we don't need this part, right? We can simplify this model and get a different model, right? This is the mathematical representation of DC motor. For our analysis, this one is too complex and too many variables, but by changing the controller of this of to the motor, by changing, I will bought more expensive controller, right? That will eject specific currents to the motor, right? From that, the advantage is the modeling part will be simpler, right? So what will be the model then? What will be the model then? Wait a minute. I think I have to add another paper. PDF. Wait 1 second, okay? So I will print this. Right. This is my simplified mathematical model, right? In here we have K, right? That is KT in here, right? Motor torque constant. In here we have Tm, right? Ts, that is load. That is the load. Right. In here, load is separated into three parts: inertia, internal load, external load, and the static friction. And this part is viscous friction. Right. This is J S. Right. So I will describe this model and ask you to do a mathematical representation of this in Python, right? You have to build this model in Python, right? We can model this one in MATLAB also, right? We can model this one in MATLAB also. How do we model this one in MATLAB? Oh. Right. This is how we model this one in MATLAB, right? We have Ka transfer function. This one is the inertia. We divide it by some value, right? Right. And what I need to do is model this one in MATLAB. So in order to do that, I will first explain this model, right? So we have injecting current. This is my command, right? This will generate using a motor controller, right? This will generate using motor controller. So we will provide inputs to the motor control also, right? Right. This is only the plant. No, this is only the plant, right? Right. This is KT motor torque constant. This one is motor torque constant. So you guys also have to write this down model. So follow me to the process, right? This motor torque constant. Now by multiplying Iref by motor torque constant, we will get the force, right? Motor torque constant is something like N over A, right? We have 24, right? KT, something like that. If we multiply this by 1 amp, we will receive 24 Newton, right? Multiply this by 1 amp, we will get 25 Newton. So this one is the torque, right? This one is the torque. In here we get the torque. And this part is also in Newton, right? This is torque load. This is the load of the motor. Internal load, external load. This one is the static friction. And this one is viscous friction. Right? And that is J, inertia. That I will not go into discuss. And this part is velocity. From right now we have the force. In here also we have remaining force of the motor, right? Remaining force, right? Got it? By dividing it to J, right? I will wrote down that one, right? I have remaining force, motor acceleration force. I will divide, right? I will divide that by J, F over J. What will I get is acceleration. So this part will be the acceleration. 1 over J will be acceleration, right? I divide that part 1 over J. I divide that part from 1 over S. 1 over S is integration, right? This is acceleration, and by integrating it, we get the velocity. Right? Got it? Right. By integrating again, we get the position. Right? That is how we read the diagram.
It's 1 over J was F over J is acceleration.
F over J. 1 over J means this, from here we get the force now. From here we get the force, right? We multiply force by 1 over j, right? Then we get the acceleration. Okay.
For JS integration, we can get velocity.
Velocity, yes. This, from this we outputs acceleration. By integrating it, we get the velocity. By integrating it again, we get the position. Theta is the position, right? Hope your notes are very clear, not like mine. Okay, right. Let's go into implement. Our topic is implementation. So let's going to implement this model using Python, right? So what I need you guys to do is, we have two guys who don't have access to do the activity now. So what I need you to do is go for Google account, right? Then search Colab, right? Then you have welcome to Colab Google Research, right? I will open this one, but you have to open new notebook. Right. Okay. Hope everyone has. Go to Colab, Google Colab, and open new notebook.
Wait little bit.
I didn't hear you clearly actually. Someone said.
Wait little bit.
Ah, okay. Okay. Oh no, this will lead to. This will lead to the. Yes. So we have 1 hour to do a lot of things. Right. Now everyone is ready. V transfer link. I don't have V transfer. No, this program is not that large, right? It is.
There is a window. Welcome to core
Collab.
laboratory.
Yes. Use
Yeah.
then that right bottom there is new notebook, right? Create new notebook.
There is mentioned file, edit, view, insert, runtime tools, help.
Yes, file, edit, view, insert, runtime tools. Those are not necessary for us now. Only thing is necessary is connect. You can connect, right? Click the connect button. So it will say it is connecting and it will give you some RAM and disk image, right? Some space to program and the
Yeah.
RAM, right? So
Yes.
what this is this is a Python platform provided by Google, right? So to us to do a program on their servers, right?
Oh,
We
okay.
can do whatever the program we need to run on their servers. So
Okay.
this service is free, but it has some limitations, right? So you can only run a program up to 24 hours and you have only, I think, 16 GB RAM, something like that, right? That for us, this is
Then
totally fine, right? So so if you are familiar with Python, we can do some Python program here. So I will tell, right? Print
so
1, 2, 3.
then it's showing RAM and disk. Then now we have to do.
Now we can do the program part, right? In these lines, we can write the program, and if we need to write some text, we can write some text also, right? It will not run, but it just text, right? In the highlighted, the black one with the arrows are the program editable program writing section, right? And this section is not a program but the letters, right? This one is called a Jupyter notebook, right? That is the original name, right? But we don't need to know everything, anything. We can run a program, right? So I have a guideline to you to do the program. So I will show my program also, right? This is my program, right? So I add the image and write some steps to follow, right? In here there are steps I follow, right? So first you need to import numpy as numpy, right? Import numpy as numpy np, right? So first do that.
So please explain again little.
Okay. In here we can do the program. If I ask you to download Python and install some large software to do the program, it will not help. So this is online tool to us to model this motor in a Python program, right? About this software, right? The Colab, right? So in this cell, we can do some programming. So if we can type something 1 plus 1 and it will output the values, right?
Okay.
Right.
Okay.
The system is running on Python. So in order to program, we need to know bit of Python, little bit of Python.
Okay.
Right. Oh, that can you tell that who haven't studied programming from your BSc time?
No, we haven't used. I haven't used Python.
You haven't used Python. If you know that C, but any programming language,
In only instruction. Yes.
right? How about others?
We haven't used Python, but
Okay.
we have used C, C++, VB.
Okay, that is good enough. C++ C is good enough. What about
So,
others?
sir, you have imported NumPy as NP,
Oh, yes.
but in our case, we don't have any file called NumPy. So, is that inbuilt
No.
file on?
Yeah. You don't need to do that, right? It is a secondary step, right? Just write down what I was right here, right? It will work, right? It just works, right?
But we cannot see anything.
Yeah, you cannot see
It shows
anything.
that we.
Yeah,
Okay.
it is for at the last step we need to import numpy as numpy, right? This library, right?
Okay.
Not to avoid collisions. Up to that time, I just import that one, right? So it doesn't show anything. It's just there, right? So now first I need to do you guys to do is initialize the parameters, right? In the motor we saw we have two values, right? Motor torque constant and the motor inertia, right? Can you initialize the values in here, right? kt as 0.134 and J as 9.1, right? Right? It's just there, right? If we need to print KT, we'll print KT, right? The values are there. We need to print J, that J, this J. Okay? We can print J, right? So what I tell you to do is initialize the other values also, right? Again, one thing I need you guys to do is this is my email. This is my email and share your drives to me. How to share? You can use this link. Click here. And this is my email. Right? You type my email here and put send. Okay. Okay. Now initialize these values. B, TF. TF is viscous friction factor. Sorry, that is static friction. B is the viscous friction, right? Initialize those values.
Can you please show me how you have shared it with your Google Drive? Okay,
In here, share. You copy that link. I share using that Teams. Then copy it to here and send.
Okay. So basically, we need to mention your email address over here.
Yes.
Okay.
Right. I use Python just to give you a brief idea. So if you need to program some robot in Arduino, you don't have to study whole C++ and C from the beginning, right? You just have to Google what you need to do in C and study at that time, then you do the program, right? In here also, if you need to do something initializing variables, just initialize variables. Okay. Don't think about whole Python, studying whole Python, those things. Okay. So, right. If you are finished initializing B and TF, static friction, then initialize forces, external forces, if external, right? If external, 0. If internal,
0. Right? That's it. Right? Right. Now initializing work is done. What else we need to initialize? Right? We have to initialize the time constant. That is the time the controller will run a full cycle, right? There is a program running time. That is the DT, right? So we write down DT as 120 microseconds. It cannot detect the microseconds, so we have to write down as 0.00120. So can you mute yourself? Right. 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 Now we have initialized the time. Now we have to initialize these two also. Motor input.
Sir, do it slowly, sir.
Okay. Do it slow. We don't have a lot of time. I have only half an hour to do a lot of things. Okay. All right. Torque external 0. This 2 you have done. This is DT. You have done that one. Right. Command velocity 1.0. Right. 501, anything. Right. Motor velocity 0. Right. Right. I think you have done this part. Right. So next what we need to do is identify the stages we need.
Command velocity on to type.
Yeah, we need to type command velocity 501, something like that.
Wait, sir. Wait. Is it?
Yeah, this is not going to work. That Rashid, can you send me your Gmail?
Okay, sir, I will send you.
So I am sharing my document to you guys, so you can access to the code. Otherwise, it will take maybe through 2-3 hours to do the program, right? So we don't have that much time. So I hope
have sent it.
you have sent it to the chat, Zoom chat.
Yeah, to the chat.
Right, now you have access to the codes, right? So what I did was, in this code, I program this model in here, right? I program this model in here, right? We have the variables. You have done that part, right? You have done that part. So this is, I will explain how I program the controller, right? So in here, iref is there, right? IA, iref something, right? I will call this one is iref. Iref is, I command as PID output. PID part I will explain later, right? Then iref is equal to, if we multiply iref by KT, we get motor torque, right? I told you this one is motor torque, right? Right? KT multiply this by, we get the motor torque, right? What will happen to the motor torque? This one is plus, this one is minus, this one is load torque, right? Torque external plus static torque. This one is viscous torque, right? Viscous friction. Viscous friction part comes with, we have to multiply B by motor velocity. Motor velocity is actual motor velocity. This one, theta, B theta, right? Motor velocity, right? Do I need to explain slower, or this fast is enough, right? Right? I get this TL as load torque, right? Torque external, torque internal also there, but it is 0, right? Torque internal, torque external is there. And torque external, internal. TF means static friction. I have the value for TX, right? I have the value for TF, and B, I have the value, and I have to multiply it by motor velocity, right? Right? Now we have done this part, right? Now we have to get the remaining force, right? Remaining force is remaining torque. Remaining torque equals to motor torque minus load torque, right? Motor torque is the previous step. We calculate the motor torque and we calculate the load torque. We reduce motor torque, load torque from the motor torque, and we get remaining torque, right? Got it? Got it? Then I discuss about acceleration. Then I discuss about acceleration, right? Motor acceleration. Now we are here, right? Now we are here. You can see the mouse point, right? Now we are here. Now we are here, right? We divide remaining torque by J and get the motor acceleration, right? Right? Then in order to get the velocity, I multiply motor acceleration with dt. Right? Now it is not correct, right? This should be an integral. To represent integral, I had to add motor acceleration acceleration times dt and add existing velocity to the integral value, right? This is existing velocity by acceleration times dt. This equation is, I hope you remember, v equals u plus at, right? Right? V equals u plus at. That is the equation. This one. Motor velocity, existing velocity u, motor acceleration times dt, right? Motor velocity, right? So what we are trying to do is control the velocity, right? We stops here and we don't need to calculate the position, right? Right? Understood? Everybody understood? So hope you can do your own program, create your own program and do the calculation. Can everybody do that? If you don't understand, let me know. Okay, I will explain again. And that this one is the motor, but the spring damper you have to implement by yourself, right? Right? If you don't understand this, let me know. Okay. Right. So I get the values from motor velocity, right? I get the values from motor velocity and I add those values. I write those values to in a, right? Though this part is, we can say, motor, right? Motor plant, right? These four. The other parts, this part is for plotting the variation of the velocity. I recorded the velocity, then I used that recorded values to plot the velocity. Right? This part to plot the velocity. Right? Right. Okay. That is done. Right? Now we are moving forward towards the controller. Right? So I told you we have a plant. We implement the plant, right? We have 4 feedback elements: controller, inputs, and error detectors, right? In here, we get that transfer functions, no? SXO, FX. Those are the plant, right? In the motor control, we implement the control sequence, right? In here, we input current and we output position, not the position, but the velocity. Theta dot, right? We input current and get the position, right? Then we feedback it to a error detector. We have input theta command CMD. We have an input and the error signal is generated. Error means this term is created by plus minus theta dot command minus theta dot response. Velocity command minus velocity response. Right? Right. We do that programming part also here, right? Inside the PID, we have error. velocity error equals commanded velocity minus motor velocity, right? Now we are here. Then we have the controller, right? So I will now discuss about the controller part, right? So, right, we are going to use PID controller, right? What is PID controller? Can someone tell me what is PID controller? Never heard of PID controllers? Right. It is a simple controller, right? It is a simple controller, but very powerful, right? Bit powerful, bit simpler, easy to tune, easy to work with, easy to program. That is why it is popular, right? Powerful, simple, right? What it does, it converts error to actual signals. Error to, he gets error, right? From the feedbacks, we generated error, no? It converts error to plant input signals, plant commands. It converts error to plant commands, right? So how do we plot error, right? So we have something like this, right? We need to achieve one. This one is velocity. This one is time. How it will get to this value? It will go to this value slowly, right? Now, if we try to achieve velocity of 60 miles per hour, kilometers per hour. So how do we achieve that speed, right? We slowly increase the velocity, and by around 55, we reduce the throttle and get to 60, right? Think of, we are going in highway in Sri Lanka, we try to achieve 100, right? That is the maximum limit. So what we do is, we get the velocity, we change the gears, right? Then we go to around 80. We go around 80, and we not try to exceed 100, because after 100 we get some tickets, right? Some special tickets, right? So we not try to go there, right? So this is how the actual value varies, right? Inside the motors, this is how the actual value varies. You don't need that, right? For our example, it is 1. We are achieving, our velocity varies something like that, right? But then I need to know how the error varies. That now my value is 1, actual value is something like that. This one is actual, this one is command. So what is the error vary? How the error varies? This is the first error, second error, third error, right? This is how my error varies, right? So I can plot a graph for error. I can plot a graph for error. So my graph will showcase something like this. Error is something like this. not something like that. I start with no big error. I start with big error, right? Then error will reduce. Right? I start with big error, then error will reduce. Right? Now we have smaller error in this area. Right? I name this one as error type. Right? So, right. First, I will tell my controller if you saw big error, right? If you saw big error, use that error to get the gain, right? Gain means generate actual signal, right? What it does is it get the error value E1, or we can say this is ET, ET1. We multiply by some value and generate the output. Controller output, right? Got it? Right? Multiplied by some K value, and this is the error, and we get it sends to the motor, it sends to the plant, right? This is error multiplied by K, right? We call that a proportional control, error-based control. If error increases, the signal increases, right? Error increases, signal increases. Error decreases, signal decreases. It is called the proportional control. Will it work? Yes, it will does. Right? So what we are going to do is study the PID controller. So before that, I explained the proportional controller part, right? Right? So in the proportional controller, PID means PID, right? Derivative, integrative, and proportional, right? What I explained this here was the proportional control, right? We get the error ET, we multiply it by KP and get the PID, P out, proportional out, right? Right.
Excuse me, sir. I have a small doubt
Yes.
regarding the previous program which you were given me.
Okay.
For the top initial, you have assigned the duration or the parameter is TF 0.00 and BG 0.00.
Where?
It's in the top initial.
Top internal. Internal.
Oh, sorry, internal. Okay, fine. Right now I'm clear. It's also 00, right?
Yeah,
Okay.
it's also 00.
I forgot to define it. It was given a name error, so I defined. Thank you, sir.
Okay.
Sorry for interrupting.
Okay. Right.
Can you share this program?
Yeah, I already shared.
Okay, thank you, sir.
Already shared. So you all in the list. Yes, everyone is in the list. Right. It took long time. We don't have that much time. Because of that, if I ask you guys to do this program, it will take hours. We don't have that much time, right? So I will give this one as an assignment. I will give another program you guys to do. Okay. I am expect you guys to another program, right? Doing another program, right? Right.
Okay, sir.
Now we have error program, error that now actually we can achieve 100. Okay. From our example, we can achieve 90 around using this proportional controller, right? We are looking at the meter, right? We are looking at the speedometer. Somewhere there we have 100. This is 80. So that we can come around that, right? Right? Actually, we can go up to 100, but sometimes if we are climbing hills in highway, speed drops, right? Speed drops. If you are going downhill, speed increases around 120, right? This should not happen, right? So because of that, we are going around 90 or 80, right? So how do we achieve actual 100? So we have to see more than the meter, right? We have to see more than the meter, right? We can achieve this one, right? We can achieve this one, right? We can achieve this one, and this will be our speed, what we see, right? If we need to gain this small portion, right, we need another value, right? That value is time. We need to know how much time we are doing this small error, right? If it is a flat surface, flat area, right, we can see now we are going constantly at 90, right? But we can increase little bit and we can go 100 actual, right? Sharp 100. So what we can do is we wait some time, right? We increment these errors, right, by using time. We increment these errors and increase the velocity, right? Right. What we do next is get the incremental value of this. Up to this, we increment the error area under the curve. Right? We increment the error by time et with dt, right? Small values. We get the value of this, and here we get the value of this, right? Get the value of this, and we increment, right? We multiply this by another factor. We call that ki. We multiply this by ki. This is the integral control ki. That one is proportional p out. K out, sorry, I out. I out. Right? Got it? Right. Let's discuss about the another controlling method, right? Inside there, we have derivative control also, right? In PID control, we covered the proportional control and integral controller, and we have derivative controller also. What that does is, right? You are not the driver now. Now we have that SLTB driver in highway. His velocities are oscillating something like this, right? This is how he oscillates. He going for 120 once and going for 90, right? Going very fast and slow also, right? What this should do is he should know how he should predict the future, right? What he should do is he should predict the future. If I am going this acceleration, right? This is very bad driver, right? this acceleration, I should end up in 120, so I should reduce my acceleration, right? That's what I should do, right? So to be to make his a good driver, you should know his acceleration and deceleration without going 120 and 75, something like that, right? So to predict the future, get the future values, we need the derivatives, right? We need the slope of his acceleration and slope of his derivation, and use these to get the predicted values and get it corrected, right? So we get the derivative det, right? We get the derivative, right? From that we can see the slope of his acceleration and deceleration. From the slope we multiplied this by kd, right? From this we get d out, right? Derivative out. Got it? Right. We can add these three together and implement inside the program. So how do we add this? The kp times error et plus the integral. So we have to another step, right? Ki et dt plus kd times d et, right? dt, right? This is my PID controller, right? This is my PID controller. Okay. Right. Right. Let's try to implement this one on Python, right? So how do we implement? So implementing is simple, right? We get the error value, error velocity, command velocity, motor velocity, right? From here we get the error, right? From here we get the error. Velocity command, velocity output, and feedback, we get the error, right? From the code, we can get the error, right? This one for error sum, to get the velocity error sum. For this part is okay. Let's do the proportional one. This one is the proportional one, right? This one is the PID out is PID out is equals to KP or KP times error plus Ki times integral error plus this is the integral error sum, right? Error sum getting by this function, error sum equals error sum plus error velocity multiplied by dt, right? This is how we program integral, right? So I will error derivative. So I need to know now the error sum is multiplied by Ki, we get the right I integral out, right? This is integral out. For the derivative, this is my equation. I get the previous error, and the new error velocity minus error previous divided by dt, right? Divided by dt. I get the error derivative. Error derivative goes here. Right? At the last, we program error previous equals error velocity, right? That is how we program the PID in Python, right? Everybody understand? Everyone understand? So we need to initialize these three values, Kp, Ki, and Kd. How do we initialize those? Kp, Ki, Kd. And error sum, error previous. Def. Error def. Right? For the PID, we need to do those. Right. Right. If we have those in the function, now we can run this program and get the outputs, right? Now we Kp is 2, we don't have plot anything, we can run this code and get the output, right? Let's run this one. Something like this came. Right? So now we have very smooth output, right? So shall we increase the Kp little bit? So now what I going to discuss is, now we done this part, right? We have now using these three values, right? Using this proportional controller, now we have Kp only, right? We have Pi only. That means Kp out plus I out, right? And proportional derivative controllers, P out plus D out. Only integral part. In here we have integral part and we have D part, derivative part, right? At the last we have proportional, integral and derivative parts, right? Then now what I am telling is you have to choose the controller for the specific task, right? You have to choose a controller for a specific task. PID control, we have K P out plus I out plus D out, right? We implemented this one, right? We implemented this one. Then we make Ki equals 0, Kd equals 0. So we cut these two. Now this one is only working, right? for the application, we have to do this adjustment. We have to first make this 0 and increase this step by step, right? This is a repetitive project work, right? Right. How do we tune the system with PID control? How do we tune the system with PID control? Right. So I will explain the empirical methods used in the program. Then I will give Sega-Nicholas tuning methods also. Okay. There are also root-Lucas method also there, but it is not easy to study, not easy to do the actual. If you are designing a system, you can do root-Lucas method, right? If you are practically implementing that Sego-Nicholas and empirical methods is the methods to tune the PID, right? So that advantage of Sego-Nicholas method is you don't need any experience to tune the system, right? Using, if you are, that easiest method is use the empirical method, but to tune the system you need little bit of experience of tuning PID controls, right? So get the experience, you can use this Python program, right? So let's see what happen if we now we are I am going to trying to tune the system using empirical method, right? So we get the values. Previously we had 2, now I am getting 4, right? It gets drastically reduced. The time is very small, so we can increase more PID. KP 10. Right. Now we have some unwanted oscillations, right? This is not good, right? This is not good. So let's increase little bit further. Right. This is the disaster, right? First, our system is working, and sometimes later it collapses, right? It collapses, right? Right. Let's reduce this to 30 and see what happens. Okay. Still collapse.
5.6 is optimized.
What? Yeah.
5.6 is optimized.
5.6. No, I try to show you what will happen, right? If we change the
Okay.
if we change the KP, this kind of things is happening, right? So for Sego-Nicholas method, you need to get 11 is not good. 11 is good, 12 is not good, right? So if we are trying to do this in Sego-Nicholas method, we need to find a value that gives, it's also not good. So let's think the stable value is 11, right? Only stable value is 11, right? So this is the maximum that KP can go, right? This is the maximum of KP can go, right? We remember that one, right? We write this down here. So that we say 5.5 is the maximum you can do. Right? Let's try that one. All right, 5.5 is pretty good, right? So let's try to increase bit more. 9. Right. So what will happen if we introduce D to the system? I introduce D to the system. It also collapses. Right. So So I think in these systems, we don't need any of those, right? We don't need any of those. IOD. Right. I think 5 is the optimum value and there is no error. So we can get the value, right? For this system, we try to tune this using empirical method and only we need Kp equals 5.5. We can get the maximum value, right? Optimum value, right? So how do we tune using empirical methods? First, we make Kp equals around 1, right? Then Ki to 0, Kd to 0, right? Then we increase this one. First step is 1, then 10, then 100, then 1000, right? We get, if we get something like this, right? Increasing an oscillation, right? Sustaining oscillations. Now we know, now this is enough, right? What in that system, that is specific system, we didn't have those. We have reducing oscillations, then collapsing, right? We don't get, it should be there, right? 11.23, something like that. We get that kind of oscillation, right? That is called critical values. We call that KU or KP critical, right? If we have those kind of oscillations, we have to reduce the values from here, right? Kp values. This is the empirical methods. Then we introduce di and dt to the system, right? So what ki will do is, if your system is oscillating and stop something there, what we need is this, right? This is our command value. What we response is this. Now we need to introduce I. 1, 2, second step is 2, something like that, right? To reduce these oscillations, we can introduce D also. 1, 2, something like that. But it can be varied, right? It can go up to any value, right? But normally, Kp is the first thing we need to study, the Kp, vary Kp and study the system, right? If you, after you done some 5-10 times the thing, the variation of Kp, you can see Kp is not suitable for this operation. Kp is not enough. Then we introduce Ki, right? If the system has oscillations, then we introduce Kd, right? Right. Then I will go and discuss about Sego-Nicolas method, right? So we don't have much time, right? So we discuss about this sustaining oscillations, right? From the sustaining oscillations, we get Kp critical as Ku, right? We increase the Kp values and get this sustaining oscillation. For this example, it is 11.2, right? Right. Also, we calculate this time interval. We call this Tu, right? That oscillation time, from this we calculate the Tu. Right? Any graph, velocity, position, force, anything, right? Then what Sego-Nicolas said is, okay, you have those two values with you. Then how do we tune P only systems? You have only P controller only, right? We have PI controllers, PD controllers, and PID controllers. Right. Now we have, I will remove this. We need those. Right. KI, KD. Right. If now we have KU and TU, right? We have those values 1.2 and 2 will be 0, something like that. I'm giving this as an example, right? Not the actual value, as an example, right? Then you have KD. For if you are using proportional controller only, right? Only the KP values, you can see 0.5 times 0.5 times KU, right? Half of KU. In here, our values is 11.
You mean?
KU means that maximum KP you can achieve with sustaining oscillations. Our output for that example we have executed on Python, we didn't achieve that sustaining oscillation value, but we know it is around 11.2 and 11.3, something around that area, right? We tried 11 is that decreasing oscillations, right? Something like that, decreasing oscillations. At 12 we get this type of oscillation, right?
Yeah.
Right. So we think our KU is around 11.2, right? So
Maximum oscillation is it?
not the maximum oscillations, but the sustaining oscillations. So you will see your values are keep oscillating like this. It will not going up.
Okay.
It will not going down. It will not going down. It will keep oscillating like this. Right. While you achieve this, you have to increase the KP and get the output. Right. Right. Then you have the KU. So after you get this value, you calculate this distance, this time distance, right? That is TU. Right. I don't calculate that one. I just giving that value as 0.002, right? As an example, right? We don't have the values here, right? If you have P and I, only P and I, the second class said this should be 0.45 KO and KI should be 0.54 times KU divided by TU, right? We don't have this one. PD 0.8 times KU. Only proportional and derivative. We don't have integral. Don't have integral. Right? This should be 0.1 times KU times TU. Right? With all the values, KI, KD, you need 0.6 KU, 1.2 KU divided by TU, 0.075 KU times TU, right? You don't have to remember this thing, right? There is no exam. I am telling this for the completion, the course, right? Right? So this is the assignment. So this is the assignment. Right. This part has to we have to skip, right? So I will do that part in separate lecture another day. Right? This is the assignment, right? Now we have discussed this system and implement the controllers, right? So I think you can do this one, right? Implement this one in Python, right? So you should know F is equal to this PID. PID, right? So I am writing just some equations. Using that, you can do the calculation, right? Then separately you can calculate this one, right? Spring force equals K times KD times X. X means we can say that one as position, right? Then spring damper force equals, now that one is the damper. This is S T equals position minus position previous divided by dt, right? Then you can write down F minus this part spring force minus damper force equals M times X double dot, right? Right? Something like that you can write down. Then using that you can tune the PID, right? So I will give some values, right? I will give some values. M equals 1, KD equals KD equals I think 2, yes, we can get the both values, both using, we can get the same results using MATLAB and the Python, right? So I am giving you to do the Python program because in the practicals of this subject, right? We don't have exam. No? In the practicals, you have to implement PID using C program or Python, right? In order to get the experience, I am telling you guys to do it in Python, right? So doing MATLAB is not wrong. Actually, it is correct, right? So we are not designing a system. We are implementing systems, right? So I will give this value as 5 case equals 6, right? Right. If you remembered, my transfer function will be xs divided by fs. This will be 1 over s squared plus 5s plus 6, right? That will be my transfer function, right? So you can do the simulation in Python. So, right, get the values. I need you guys to get the same values by computing this on Python and tuning the PID values and get same results, right? So that is the assignment for this subject, right? So you have to do in Colab, and while you are doing it, you have to save your program, something like that, right? Go to files, save and pin revisions. Not the save only, save and pin revisions, right? So if you do that, I can check the if you are copied or not, right? Those are the pin revision, right? See, so I should see some long pin revisions. If you changing KP, save as a pin revision, get the output. Again, change the KP, save as a pin revision, right? Do that and send to me. Okay. Not sending, but you have to share, right? Your file name should be your index and spring damper. Your index file name should be index
Excuse me, sir. When I go for sharing this one,
yes.
it's showing some links only. Unable to upload your mail ID to share the link.
What?
So in that case,
No, you can share
when
using that one. No? I don't need to.
can
You
you show me only one time?
and you can go here, share. You can add my email address. This email address. In here.
For me, it's something showing like a notebook link, not the same visa you're having to add the mail ID and some stuff like that. But since already I have logged into the Google account.
Not you are not logged into the Google account.
I have already logged into the Google account. It's showing my Google account detail.
Okay.
But since when I'm going to the share, it's just only saying notebook link, and it has given a one link. Maybe the link for this kind of a
Link
program.
also that is also fine.
Okay, if I send you the link via email, is okay, right?
Yeah.
Okay.
Right. Hope everyone got the idea how to do the assignment. I know it is hard, but don't worry. You have the example code, right? I ask you to repeat the same thing, right? This part is repeated. This part is repeated, right? In these two values, these two can be replaced by position. This should be a position, right? This should be a position, and this dt is the same, right? And it's the same. This will show the plot, right? This will generate in the plot, right? I imported this numpy as numpy in order to
How to
create.
generate the plot that
Yeah, from this part you can generate the plot, right? Without that part, it will not generate the plot. It will just generate the values, and we are not showing the values now, so it will disappear. So what I did was I created this one, right? I created this one. This val means value. It is a error. So numpy array, right? It is a numpy array. Array means we have 100 rows and 2 columns. I will show you.
If you need to increase the array size, how you can do it?
Yeah, you can increase the array size. Okay, I will show it. Right now, this is how I initialize the array. This is how I initialize the array. Now I changed the for loop into 1000, but my array is only 101. So I have to change that one also to 1000, right? Then I can run it. So we just extend the time limit. Right now it is showing 1.2 seconds, right? So if we increase more, we have to increase the array size also, right? 1000 rows, 1000 lines, 2 columns, 1000 rows and 2 columns. Now it is 10,000 rows, 2 columns. Now time is 1.2 seconds. Previously it was 0.12, right? I can reduce it also, right? I can zoom this and reduce this also. Now I am zooming to 100, right? Then only I can see the variations, right? Then only I can see the variation. I think I can reduce it to 50 also, right? 50. And this one is 51. Right? Now I can see the difference, right? The curve. Got it?
Yes, sir.
Right. So I will give, I think today is Sunday. So from how long do you need to submit the
You sometimes, sir.
give sometimes
So we
2 hours?
no, we having some. It's okay, sir. But we having some other assignment also. It's nearby the due date, and also
Okay.
some presentation for the projects and some steps are there.
Okay.
Better consider that one. But we are not falsely asking like we need this particular device
Okay.
or something. Just
Okay.
consider into that.
Okay. I think we don't have lectures in 30th. We only have lectures in 20th, right? So can you guys submit that one in 19th, Saturday? It is not 18th is good, right? I think.
Okay.
Right? It is not a
So, okay.
hard submission day. You can send it. I think it is better you can submit within 2-3 days, because after a while you will forget how do we achieve these codes, right? That
Okay, sir.
that exam that in class I gave, that test I gave, it is much similar, right? But not that much complex. It is not that complex, right? Only 3-4 equations, right? 3-4 equations. PID part you already have, no? Only these 4 equations you have to implement, right?
Okay.
The assignment is based on only for this damper
Yes,
calculation, am I right?
yes. You implement this system and you have to find out the KP, KI values also, right? I already gave that secret method, right? I already gave the transfer functions. If you are familiar with the MATLAB, you can get the values, PID values. So you can auto tune the PID values and get the PID values. I'm not telling you guys to do it. If someone can do it, it is good, right? Already I will share you the some links.
This
I will,
lecture also upload in Noodle.
yeah, I will upload the lecture also. I will share these 2 links, right? So those guys from the YouTube, you can also learn how to tune the PID, right? So if you're not completely miss the what I was telling, I think you cannot miss that, right? There is no simpler way to do that, right? So you can learn that by from the YouTube, right? So that guy is also that I know this one very clearly. You cannot find the PID programs in Python, right? You cannot find that in internet, right? You have to do that in your own, or you have to copy one. If you copy that one, I can identify the copied program, right? Right. So don't copy. Try it by yourself. You ask friends how to do the program part, right? Only 4 equations. You take 1 hour to study the program, right? Take another 1 hour to write down the equations and tune it up. Then it is done, right? It is not that hard question, right? If you copy that one, I can easily identify it, right? Okay.
And also, can you please share how to make the revision of the software?
How to
Make the revision of the Python software.
revision. That is if you save, if that you can save this file, right? This is that your program, this is untitled 01 something. No, you can change the name to your index, something like that. Then spring damper, right? That is your name should looks like, right? Then you have to do file, save and pin revision. If you do some changes and save and pin revisions,
Okay, thank you.
right? Not the save and pin revision. Okay.
Okay.
So then it will change, it will save the changes you did, not the full program, but with the changes you did, right? If I saw the revision history, I can see nothing in here, nothing in here. I can clearly see this guy is copied somewhere else and put it here, right? This is that image, right? This is that image. This part is the code. This part is the code, right? So I will tell you, right? So do the program step by steps. You only have to write 4 lines in here, right? Everything else is there, right? So I took extra half an hour. Sorry for that. So we will see you guys in the next week.
Doesn't matter for taking how long time for studying, sir. And thank you very much for your valuable lecture. We have learned a lot here.
Okay, right. Thanks. Right. Right. Thanks for participating. Okay. We will see you guys in the 20th February, right? Next lecture.
Thank you.
Thank you. Thank you.
Have a good day.
Thank you, sir.
You're all welcome. Stop recording.